Okay, let's remember exponentials and logarithms. So exponential function is where we usually have the rate or proportion raised to an exponent. There's a general form you can think of. You can always think of a starting amount and then some type of rate or proportion, but usually it's written as f of x equals a times b to the x. So b is kind of like that proportion or that rate, and a is the starting amount. Okay, so an example here would be f of x equals 2 times 3 to the x. So 2 is where this thing starts at, so it kind of has the point 0, 2. If you plug 0 in, you'd have 3 to the 0, which is 1. So it just leaves you with the 2. And what's happening here is as you increase x, you're multiplying by 3 each time because you're increasing the exponents. 3 to the first is 3, 3 squared, 3 times 3, 3 cubed, 3 times 3 times 3. So essentially you're multiplying by an additional 3 every time you increase x because of the exponent, which is basically causing this function to triple. Okay. As opposed to the function 3x plus 2, which is linear. So even though it says 3 times x in a linear function, every time you increase x, you're really adding an additional 3. You might be multiplying to do that addition, but every time x increases, you're just putting in another 3. Whereas with the exponential, every time you increase the x, you're multiplying by another 3. Okay, so let's see here. Let's just do a quick graph of the exponential function. 2 to the x, just so you can see it. So 2 to the negative 3. That's 2 to the negative 3, 1 over 2 to the third, so 1/8. Very small. 2 to the negative 2, 1/4. Okay, remember what negative exponents do. They take stuff to the bottom. So let me go back. 2 to the negative 3 is the same thing as 1 over 2 to the third, and that's where the 1/8 come from. Okay, so 2 to the negative 1 would be 1/2. 2 to the 0, 1. 2 to the first 2. 2 squared, 4. 2 cubed, 8. So you see over here in some places it's not changing very quickly with the fractions, the 1/8 to the 1/4 to the 1/2. But then as we get on the other side of 0, we multiply by 2 each time. So 2, 4, 8, those are getting further apart. One of the main things here to compare yourself to the linear function is to notice that we're not changing by the same number each time. But trying to put these on the graph, negative 3 gives me 1/8, then negative 2 gives me 1/4, negative 1 gives me 1/2, and then finally at 0 I get 1. And then continuing on, 1, 2, 2, 4, and 3, 8. So we see this function changing very slowly in the beginning, and then eventually taking off very quickly. Now we can put negative numbers in for the exponent, but it's not going to make the outcome negative. So it's kind of flat on the left-hand side. And once again, this is a general shape, similar to how we graph parabolas, but that shape can be moved around and all types of things. So if I want to do a similar function, g of x equals 2 to the negative x, so in the exponent I've changed the sign, I've kind of flipped this around. So that would be 2 to the negative 3, so 2 to the third. So I'm kind of flipping all the points I had before. So if I do that, I see the same graph behavior, or at least similar, but in graphing it I start to see that it is the same shape graph, just in a different place, moved around. So this one goes down, whereas the other one went up. Okay, so just like when we wanted to find intercepts and stuff before, we need some way to be able to solve certain types of exponential equations, and that's where logarithms are going to come into play. So you have to remember your definitions and relationships between exponentials and logarithms. So y equals a to the x is an exponential form, and the logarithmic form would be x equals log base a of y. So we have a special placement and relationship between the exponential and the logarithmic. So the other ones, that's for any base. We also have, if we want base 10, the common log, y equals 10 to the x. That would be x equals log of y, and it's understood that base to be 10, so we don't write it. It's called the common log. And then y equals e to the x is x equals the natural log of y. That's understood to be the natural log base e, so we also don't write the base there. So if we don't list the base in a logarithm, it's either going to be base 10 or base e, and that's because our calculator is kind of limited. Some of them. So it says here, these relationships are useful when solving exponential equations. So we're going to solve 500 equals 10 to the x. Now you can plug numbers in for x to try and guess what it is, but it's going to be hard to get it exact. So what we're going to do is we're going to use the logarithms up here, and we'll switch it around. X equals log base 10 is understood of 500. So the solution for x would be log of 500. Now that doesn't mean a lot to us, so if we pick up a calculator, I'm going to round this to 3 decimals, waiting for this thing to catch up. X equals 2.699, and I should be able to plug that in up here for x and make the equation balance. Here's a similar one. Solve 200 equals 4 times e to the x. So if we want to do that conversion we had up top, which was, let's see, y equals e to the x can be switched over to x equals natural log of e. Excuse me, natural log of x. Go away, buddy. I mean, natural log of y, sorry. X equals natural log of y. So if we want to do that, we need to kind of rearrange this. So we're going to divide out that 4, so we'll have 50 equals e to the x, and then we can change that over to x equals the natural log of 50 and put it in our calculator. So natural log of 50 is an exact number. It's not the easiest number in the world to quantify, but in a calculator this will be 3.912. Again, another approximation. Guess is what we need. Okay, so here we have change of base formula because our calculator is very good about being ready to do base 10 and base e, but it's not so good about other bases, just the limitations of the calculator. So we have some formulas here to help us out. So a change of base formula lets us take any base and change it to base 10 or base e or even a different base, but that's usually not very useful. So the formula is log base a of b. That can be changed to the common log ratio, log b over log a, both understood to be base 10, which means you could put them in your calculator. Or the natural log ratio, natural log b over natural log a, both understood to be base e. So, in practice here, we're going to evaluate log base 4 of 75. So the a is 4, the b is 75. So we could write this as log of 75 over log of 4. Or we could write it as the natural log of 75 over the natural log of 4. But either way, we'll put it in our calculator. And let's see what it gives. So you can try both ways if you like. But I get 3.114. Like I said, you could try it differently with the natural log if you like, and you should get the exact same thing. The other one we'll do here is an equation. 21 equals 3 raised to the x. So x is probably more than 2 but less than 3 because 3 squared is 9 and 3 cubed is 27. Excuse me, so it's probably in between there. But let's rewrite it. So we'll have x equals log base 3 of 21, but for most calculators that doesn't go in. So x will be, using a change of base formula, log of 21 over log of 3. Still an exact answer, but if we want to quantify it, let's put it in our calculator. And if you need help with calculators, let me know. But this gives me 2.771. Okay, and that's an approximation, probably close enough to do anything we need. Let's see if we got any more practice down here. Oh, we're ready for practice. We'll stop this video here.